Hey everyone, I'm Yogesh Kumar from CADMech and welcome to the only plastics guide you'll ever need. Whether you're a beginner or a seasoned engineer, understanding plastics is absolutely crucial for successful product design and manufacturing. Picking the wrong plastic can completely ruin a project. It's often the difference between a product that lasts for years and one that fails on day one, costing you time, money, and reputation. But when you choose the right material, your parts perform reliably, look great, and stand up to real-world use. In the next 10 minutes, you'll discover the 10 most used engineering plastics, learn exactly when to pick each one, and find out what critical factors to check before you finalize your design. This is the practical, hands-on guide I wish I had when I was starting out in the industry, and it's packed with real-world advice you can use immediately. We'll quickly meet the top 10 plastics, break down their strengths and weaknesses, and see real examples of where they're used in everyday products, from gears to medical devices. Then, I'll walk you through a simple, step-by-step selection process you can start using right away to make confident decisions. Finally, we'll cover some practical CAD and manufacturing tips so you can avoid the most common and costly mistakes that trip up even experienced designers. By the end of this guide, you'll be a plastic picking pro, ready to tackle any project with confidence. Let's dive in and get started. Let's kick things off with the heavyweight champion of the plastic world, PEEK, or polyethertherketone. This isn't your average plastic, it's a material that stands in a league of its own. PEEK is the go-to choice when failure simply isn't an option and cost is a secondary concern. Think of it as the titanium of plastics, exceptionally tough, reliable, and built for the most demanding jobs. It's incredibly strong and stiff, maintaining its shape and properties even under punishing conditions. PEEK shrugs off high temperatures, performing flawlessly up to 250 degrees Celsius, where most other plastics would melt or deform. Its chemical resistance is virtually unmatched, allowing it to survive in environments filled with aggressive solvents, acids, and other harsh chemicals that would destroy ordinary plastics. You'll find PEEK in spinal implants, aerospace engine parts, and oil and gas seals, places where nothing else will do. It's trusted in critical applications where human lives or millions of dollars are on the line. The catch? PEEK is extremely expensive, 20 to 50 times pricier than ABS. It's a premium material and that price tag reflects its extraordinary capabilities. So, use it only when you truly need the best performance and can justify the investment. For most everyday applications, it's overkill. Design tips. PEEK's high melting point means you'll need specialized molding equipment capable of reaching and maintaining those extreme temperatures. Avoid sharp internal corners in your designs. Instead, add generous fillets to prevent stress concentrations and reduce the risk of cracking during use. For even greater strength and stiffness, consider glass or carbon fiber-filled grades of PEEK. These composites take performance to the next level, making them suitable for even more extreme applications. Processing PEEK is tricky. Its high melt and mold temperatures require expertise and specialized equipment. Always work with experienced manufacturers who know how to handle this demanding material. If your supplier isn't familiar with PEEK, you risk ending up with poor quality parts full of internal stresses, cracks, or other hidden defects that could lead to catastrophic failure. Always confirm your manufacturer's capabilities before specifying PEEK for your project. Ask about their experience, equipment, and quality control processes. PEEK is not a casual choice. Reserve it for high-stakes applications where only the best will do, and where its unique properties are truly needed. Get the details right, and PEEK delivers unmatched performance, reliability, and peace of mind in the most challenging environments. But if you don't need its superpowers, save your budget for something else. There are plenty of other plastics that can get the job done for less. Next up is PEI or Ultem, PEEK's transparent high-temp cousin. Ultem is naturally amber and handles continuous use at 170 degrees Celsius, with great strength and dimensional stability. It's flame retardant, low smoke, and perfect for electrical connectors, reusable medical tools, and aerospace interiors. Ultem bridges the gap between standard and ultra-high performance plastics. Design tips. It's susceptible to stress cracking with certain chemicals. Always check compatibility. Like PEEK, it needs high processing temps, but offers excellent dimensional stability. Avoid sharp corners, use generous radii to prevent failure. Watch out for chlorinated solvents and strong bases. Ultem is your pick for high-temp, see-through, and safety-critical parts. Meet PPS or polyphenylene sulfide, the reliable, chemically resistant workhorse. PPS excels in harsh environments with top-tier chemical resistance and stability at up to 220 degrees Celsius. It's a favorite for automotive fuel systems, pump housings, and electrical connectors. Glass fiber reinforcement boosts its strength, but makes it abrasive to tooling. Use hardened steel molds. PPS flows easily when molten, great for thin parts but prone to flashing. Precision molds are a must. Fiber orientation can cause warping, so account for it in your design. PPS is stiff but can be brittle. Glass-filled grades are common for toughness. It's inherently flame retardant and a solid metal replacement in many applications. Watch for fiber alignment and tool wear. PPS is your go-to for chemical and heat resistance on a budget. PTFE, better known as Teflon, is truly the king of low friction. Almost nothing sticks to it, not even geckos, which are famous for climbing nearly any surface. This unique property makes PTFE legendary in the world of materials science, and it's why you'll find it in so many surprising places. PTFE is nearly chemically inert, meaning it doesn't react with most substances, and it can handle a massive temperature range from a freezing -200 degrees Celsius all the way up to a scorching 260 degrees Celsius. That's why it's trusted in everything from deep space missions to kitchen cookware. PTFE is perfect for seals, gaskets, bearings, and wire insulation, anywhere you need things to slide smoothly, resist harsh chemicals, or survive extreme environments. It's even used in medical devices and high-tech electronics. But there's a catch: PTFE is soft, it creeps under load, and it's not suitable for structural parts that need to bear weight or hold their shape over time. You can't injection mold PTFE like most plastics. Instead, it's compressed into shape and then sintered, which means you're limited to making simple, basic forms. No complex designs here. Bonding PTFE is a real challenge. Its slippery surface means you need mechanical interlocks or special surface treatments just to get anything to stick. PTFE is easily damaged during assembly, and its extreme slipperiness makes gluing nearly impossible. Even handling it can be tricky, as it tends to slip right out of your grip. So use PTFE for surfaces where you want things to slide or resist sticking, not for load-bearing structures or parts that need to be glued. Always watch for creep and low strength. Over time, PTFE parts can deform under pressure, unlike more rigid plastics. But when it comes to non-stick, chemical-proof, and high-temperature needs, PTFE is simply unbeatable. It's the go-to choice for demanding environments. However, if you need real strength or structural integrity, you'll have to look elsewhere. PTFE just isn't built for that. In the end, PTFE is a true specialist, amazing at what it does but not a generalist. Use it wisely, and it will never let you down in its niche. POM, or Acetyl Delrin, is the workhorse for strong, low-friction, dimensionally stable parts. It's ideal for gears, bearings, bushings, and rollers, anywhere you need toughness and precision. POM resists moisture, so it holds tolerances better than nylon. It's easy to machine and mold, with a great surface finish. Watch for thermal expansion, account for it in your tolerances. POM doesn't like strong acids or bases, and it's tough to bond, designed for mechanical fastening. Overheating releases toxic formaldehyde, so process with care. Use POM for moving parts in printers, cars, and tools. It's versatile, tough, and reliable. But always check chemical compatibility. For precision mechanics, POM is hard to beat. Nylon, PA6, PA66, is the classic for toughness, wear resistance, and impact strength. It's the all-arounder for gears, bushings, power tool housings, and automotive parts. Nylon is self-lubricating, resists oils and fuels, and is used everywhere from zip ties to engine covers. Its main challenge: it absorbs moisture, swelling, and changing properties. Designed for this. Moisture makes it less stiff but more impact-resistant. Always condition parts before use or adjust tolerances. Glass fiber reinforcement boosts strength but increases tool wear. Nylon is attacked by strong acids and oxidizers. It's tough, versatile, and everywhere, but always account for moisture. For impact and wear, nylon is a top pick. Just don't forget its sponge effect. Polycarbonate, PC, is the go-to for clear, tough parts. Think bullet-resistant glass, safety goggles, and car headlights. It's 250 times more impact-resistant than glass, with good heat resistance and dimensional stability. PC is used for protective housings, lenses, and medical devices. It scratches easily, so hard coatings are common. It's sensitive to UV. Use UV-stabilized grades for outdoor use. PC can stress crack with certain chemicals. Check compatibility. Always dry PC before molding to avoid defects. For clear, tough, and safe parts, PC is a designer's dream, but protect it from scratches and sunlight. For impact and clarity, PC leads the pack. ABS is the Swiss Army knife of plastics. Tough, rigid, glossy, and easy to process. It's the material behind Lego bricks, power tool housings, and most 3D printed prototypes. ABS balances cost and performance, making it a favorite for consumer products and automotive interiors. It's easy to mold, machine, glue, and finish. For 3D printing, control warp with a heated bed and enclosure. ABS degrades in sunlight. Use UV-stabilized grades or paint for outdoor use. It's attacked by solvents like acetone, great for smoothing prints, bad for chemical exposure. ABS releases fumes when melted. Ventilate your workspace. For prototyping and everyday products, ABS is a go-to. Just watch for UV and chemical exposure. PMMA, or acrylic, is the clear scratch-resistant alternative to glass. It's more optically clear than glass, UV-stable and weather-resistant. Acrylic is used for displays, signage, car taillights, aquariums, and architectural models. It's easy to laser cut, heat bend, and solvent weld, but it's brittle. Avoid sharp corners and over-tightening screws. Acrylic shatters on impact, unlike PC, and is attacked by alcohol and acetone. Clean with soap and water only. For clarity and aesthetics, acrylic is unbeatable. But for impact resistance, choose polycarbonate. Use acrylic where looks matter most. Polypropylene, PP, and high-density polyethylene, HDPE, are the kings of cost-effective chemical resistance. PP is famous for living hinges and fatigue resistance. Think bottle caps and food containers. HDPE is strong for its weight, used in bottles, pipes, and playgrounds. Both are tough, flexible, and resist most chemicals. They're everywhere in consumer goods and industry. Not very rigid, don't use for high-load, tight-tolerance parts. High thermal expansion and shrinkage. Design molds carefully. Hard to bond or paint, surface treatments are needed. Both degrade in sunlight. Specify UV-stabilized grades for outdoors. For budget-friendly chemical-proof parts, PP and HDPE are your answer. That's your crash course on the top 10 engineering plastics. Now you know when to pick nylon for toughness, POM for low friction, or PEEK for extreme environments. Use this as your mental toolbox for smarter material choices. Want a cheat sheet or design checklist? Let me know in the comments. If this helped, hit like and subscribe for more CAD/MEC deep dives. Plastics are a toolbox. Pick the right one and your part wins. Thanks for watching. Drop your questions or requests below and see you next time.